One final application of the law of uninhibited growth and decay is Newton's law of cooling. And so this model uses the law of uninhibited decay, but it does have a little bit more to it. And Isaac Newton worked on this and was credited with it. And so it takes into account the temperature of the surrounding air, as well as the initial temperature that the object started at. And then you can find out the temperature after a certain amount of time, because the way something hot cools down is exponential decay. So if you think about when you take something out of the oven, right? Let's say it was 400 degrees when the cookies came out of the oven, and then after a couple minutes, they're actually cool enough to touch, right? And so they might be 100 degrees by then, after just a few minutes. After an hour, they don't actually cool down to zero, do they? They cool down to the surrounding temperature, the air temperature. So they might, after a longer time, cool down to 70 degrees or something, the air temperature. So this law actually works in Fahrenheit and Celsius. So I'm sure some of you are more familiar with Celsius, but it does work in either system. So this particular question is in Fahrenheit, but I know some of your homework questions are in Celsius as well. All right, so Newton's law of cooling states that the temperature at time t is equal to the temperature of the surrounding area plus T naught, that's the initial temperature of the item, minus the temperature of the surrounding area, parentheses, times e to the kt. So there is our exponential decay right there. So let's define some of those things so we don't forget what all those t's mean. So the T of t is the temperature at time t, lowercase t, okay? Ts is the surrounding medium's temperature. So we'll just say the surrounding temp, okay? And then T naught, that little zero there again, is the initial or original temperature of the object, okay? So for example, a pizza is baked at 450 degrees, removed from the oven at 5 o'clock p.m., and placed in a room that is 70 degrees. So that's a pretty, typical thing to happen, at least in my house, right? You cook a pizza in the oven and your house temperature is about 70 degrees. Those are pretty typical Fahrenheit measures. If you're not as familiar with Fahrenheit, that's pretty normal. After 5 minutes, the pizza is at 300 degrees, okay? So 300 is still pretty hot, but it's cooling down enough that maybe you could blow on it and eat it. And notice that it did that in 5 minutes. At what time can you begin eating the pizza if you want its temperature to be 135 degrees? You don't want to burn your mouth on that cheese, right? So that is a loaded question. There's a lot we have to do before we can answer that question. Once we do all that work, the other parts of the question are pretty simple to do, okay? So let's start with what we know. So we have information about T naught, right? The pizza was removed from the oven at 450 degrees. The surrounding temperature is the room temperature, 70 degrees. The time that we're talking about, lowercase t, it started at 5 o'clock and it said after 5 minutes. So the time is 5 in minutes. And then we know that the t at time t, after 5 minutes, is 300 degrees. All of this information, we're going to plug this into the equation so we can find that K value, the constant of decay. So let's give ourselves a little more space. Okay. Okay, and then let's plug some things in here. So we know that 300 is equal to 70 plus parentheses 450 minus 70 e to the k times 5. That's that 5 minutes. Okay, so I just took all this information and plugged it into our formula. All right, so we're going to solve this the same way we have been solving these equations. So first, I think I'm going to subtract 70 from both sides because I do need to isolate that e before I can do anything else. So that would be 230 equals, and then 450 minus 70 is 380, e to the k times 5. Okay, now, just as before, divide both sides by 380. So I'm getting 23 over 38 is equal to e to the k times 5. 5k is fine too. All right, now that I have the e by itself, the base by itself, I can change to log form. So that would be ln 23 over 38 is equal to k times 5. Okay, so in other words, our k value is the natural log of 23 over 38. And then to find k, we just divide all that by 5. Okay, so we could type this into the calculator, but remember, that's going to give us some rounding error. So I'm going to try to leave it like that. Maybe in my equation when I'm writing things, I might just write k, but in the calculator, I am going to type in all of that stuff, okay? If you know how to store values in your calculator, I was thinking that would be a good thing to do. You can type this in, get the answer, and then store k. That might save you a little time. All right, so now that we have the k value, we actually have the whole equation. So I'm going to write our equation for us. That's the temperature at time t is equal to 70 plus 450 minus 70 was the 380. E to the k now we know is ln 23 over 38 divided by 5 t. Right? Our goal is always to find an equation in terms of time to model our growth or decay. All right, so it says, at what time can you begin eating the pizza? So we're looking for T if you want its temperature to be 135 degrees. Okay, so we're going to need to, we have two options. We could graph this and find 135 degrees, the value at 135, or we can solve this algebraically. I know some of you like to do the algebra, so let's put 135 as the final temperature there is equal to 70 plus 380 e to the, do you mind if I just write k? We know what k is, right? And then t is our variable. Okay, t is what we're solving for. So once again, we have to subtract 70 here. We get 65 is equal to 380 e to the kt. All right, and then we have to divide both sides by 380. Okay, so I'll just leave that as 65 over 380 is equal to e to the kt, right? And then change it to natural log form. So ln 65 over 380 equals k times t, right? Now remember, I've just been writing k because I don't want to keep writing this number over and over again, right? But we know k, and we're looking for t. So t is equal to natural log 65 over 380 divided by what the k is. And the k is natural log 23 over 38, all divided by 5. I'm going to throw some parentheses around that. Okay. And it looks like if I type all this in, I get about 17.6. And then the time that we said, it was 5 minutes, so it's in minutes still. Okay. So it takes about 17, 18 minutes for the pizza to cool off to where I want to eat it. Now, just to let you know, I'm not sure this is 100% reliable because that seems like a long time to let your pizza cool. I feel like the pizza would almost feel cold by then, right? Okay, so it says, at what time can you begin eating your pizza? So it would be after 17.6 minutes or 18 minutes. So it's about 5:18 p.m. because you started this at 5 o'clock p.m. Okay, so make sure you do understand the question they're asking. All right, it says graph the relationship between temperature and time. So in other words, this equation that I put a box around, we're going to put this in our calculator and look at it. And then we could actually do the other two questions from the graph. Okay, we can do them algebraically because we've been doing that over and over again, right? But we can also look at them from the graph. So if you don't have to show work, you could do it from the graph. If you do need to show work, then you have to do it the way I've just been doing it, solving algebraically. Okay, so let's take a look at the graph. All right, so I've typed in 70 plus 380 e to the k, which is ln 23 over 38 over 5 times x. Remember that the t is just the variable x right there. Okay, so now that I have that typed in, I hit graph. Surprise, surprise, it's not really showing up because, my window was from my last problem and it doesn't apply to this problem. So I'm going to have to go to window. And yeah, I had X max as 35,000, but that's in minutes. I don't want to know about this pizza after 35,000 minutes. Do you? So let's take the time from 0. And then I know we have to find the temperature of the pizza after 1 hour. So that's 60 minutes, but we probably maybe want like 70 minutes because we need to be able to see the 60 on the graph probably. So 70 minutes, the way I figure out my X and Y scale is I just think about what the units are. So I know the time this time is time in minutes. I'm talking about a pizza coming out of the oven. Make something reasonable. The Y value I know is the temperature of the pizza. So a temperature of pizza, I want it to go from 0. I just like to see the beginning of the graph there. But I know that my Y max, the pizza started at 450 degrees. So I need at least 450. I mean, I could make it more, but it's not going to get hotter because it came out of the oven and it's getting colder. So let's hit enter there. And then I bet when we graph, we see this nice exponential decay. Yeah, it's so important to think about what the window is, I think, in these problems. All right, so we have this lovely graph, and notice what it's doing here at the bottom. What number do you think it's getting closer and closer to here? Hopefully you're thinking 70 degrees, right? Because this is the temperature. And of course, the room temperature is what that pizza is cooling off to. Okay. All right. So it says, determine the amount of time needed to elapse before the pizza is 160 degrees. Okay. So remember, this is the temperature. The Y is the temperature. So go to Y2, type in 160 as your Y2 value. Graph. Okay, so right there is where it is 160 degrees. Let's intersect that. That's second calculate number 5. Enter, enter, enter. 3 times. And let's see what I got. I got 160 degrees for Y, and the X is 14.34 what is that, minutes. So like about 14 minutes. Okay, so I'm going to write that on my paper. This is actually part C. T is about 14 minutes. And that's from the graph. Okay, so I'm not doing that algebraically right now. All right, and then finally it says, what's the temperature of the pizza after an hour? Well, my guess, remember we made this 70 minutes, I think. So, I'm thinking it's going to be pretty close to 70 degrees is what I'm thinking, but I want to make sure. So remember, you can do that on the graph too. Second, calculate value because I need an x value this time, and that would be number 1. And for 1 hour, I want to put 60 minutes because my time is in minutes. Okay, so I got 60 minutes. It's 70.9 degrees. So D, the temperature is about 70.9 degrees. So it's still cooling off, but it's getting closer and closer to 70. That is that horizontal asymptote.